Today, my talk's going to be about dealing with medical images and medical image formats, some tools to process them digitally, and some pitfalls. But before we start talking about medical images and their digital formats, the first question is, why medical imaging? Now, this might be common knowledge to some of you, but let me go over the history of it for those of you who are not very well acquainted with medical imaging. First, why do we need it? Let me take you on a journey back around 500 years. We want to know what the inside of somebody's body looks like. How do we do it? A little bit permanently, I would say. Now, this gentleman in a 15th century painting has been taken apart so that the insides of him can be examined. And this example is a little bit gruesome, but I would also say that this is not the only way it was done. It was quite commonplace for doctors to observe wounds from soldiers who had just taken part in warfare and look through that to get knowledge of the internal workings of the body. And naturally, the information gained was a bit transient since you could not observe it over long periods of time without repeatedly invading the patient. As we can see, this person has likely been killed. How did this evolve over time? Well, there were other ways to study it. For example, if one wanted to study bones, one would have to one could take apart cadavers. What we have on the left over here is a book by Leonardo da Vinci, the Renaissance man. And he's come across these studies by taking apart different cadavers to try to observe how joints and bones work. And this is one of the studies that he came up with, detailing how the bones of the arm worked. On the right, we have perhaps one of the first books about modern medicine written by Vesalius. And one can see, even in his time, which was, I think, the 1600s at this point, almost 100 years past, one still had to observe the body invasively. In this one example in a medical university, one body is being taken apart and almost 50 people are watching to see what's inside. Now, naturally, this was not scalable and it was not effective and it was very invasive. How did this matter change? This matter changed actually quite recently. The first example of a modern medical image was not until the 1890s at the University of Würzburg, where a scientist, Wilhelm Röntgen, was playing around with X-rays. And he finally made the first X-ray image very accidentally. This on the left is an example of his wife's hand, with the bulge that you see around the finger being the wedding ring. This is the first medical image taken and the first non-invasive image ever created. On the right, you see the publication that was generated from this kind of science called eine neue Art von Strahlen, which means a new type of radiation. And for a long time, this was the only way of getting non-invasive medical images of the body. Now, naturally, when you think about X-rays, you stand in front of a scanner, you project it straight on, and the rays go right through you. The problem with this becomes that, of course, it's impossible to see cross sections of the human body. So just taking the X-ray physics and combining it with advanced mathematics, one was able to develop the CT scan. A fun fact, the CT scan was actually not invented by someone who was working in the medical imaging or the medical field at all. It was invented by an engineer working at the Beatles EMI Music Laboratories. And he used his free time to create this technology, which involved taking X-ray scans 360 degrees around a patient. This, what we see here, is a 32 by 32 brain image created by one of the first commercial CT scanners. As you can observe, one can see an axial image of the brain, so a cross-section rather than just a straight-on image. Naturally, with time, technology evolves. You used to have this, say, in the 1970s. What you have today is a bit more advanced. It's not just CT anymore. There's MRI, there's ultrasound, there's PET scanning, and there's upcoming modalities such as OCT or optoacoustic imaging, which haven't been fully yet integrated into completely clinical workflows. The amount of data being produced where computers are coming in to process these images and construct them is increasing day by day by day. And it's not a small amount of images now. There was a study shown that 5 billion medical imaging studies were conducted by 2010. We are in 2023 now. I would not be surprised if the number has scaled exponentially, and it's almost 10 billion studies at this point. Just if you open source medical images, if you Google, okay, open source medical images of any type, CT, X-ray, MR, ultrasound, there are more than 45 million images available. So we need ways to load these images, to process them, and to look at them digitally. It is not possible to manually have a clinician scan through 45 million images. It's not a small market either. The shipment of medical imaging chips, just the semiconductors, is already worth 1 billion. When one thinks about it, this market is just growing larger and larger. How does medical imaging actually play a role in the hospitals, though? Where do the computers come in? So as one can see, this is a study which shows some digital workflows in the hospital, which links the HL7, which is the electronic health record, with the DICOM images. DICOM is an imaging format, which I will discuss a bit later on. So what we have first is the HL7 patient record, and then we have the PACS, the picture archive system, which takes in images from the imaging devices and then either transmits them to various servers, storage spaces, databases, or workstations where they can be viewed by clinicians. Computers, as we see, are already playing a role. So on a broad level overview, computing and digital formats are pretty important. So now let's get into the little details. First, let's talk about the image formats. What are the various image formats that we deal with in medical imaging? The most popular image format is one named DICOM, Digital Imaging and Communication in Medicine. So DICOM is a format of storing images with the metadata used to create an image. This is a pretty old format. It was developed in the 1980s. And it's used for storing all sorts of images. It stores a 2D image within something called a DICOM series. If you have a CT scan of a patient, it will store every single cross-sectional slice as a different DICOM image in the same folder. This is used for multiple imaging formats in CT, in MRI, PET, X-ray, and even ultrasound. Now, what sort of metadata is usually stored with the image? So this is metadata, which is pretty important for understanding the context of a medical image. And here are some tags, some examples. So as you can see, the patient's birth date would be stored, the birth time, the patient's gender, the patient's insurers, and other options, age, size. There's strains as well over here, which may not apply perfectly to CT, but also something that can be taken into account. Group of patients, if someone is doing multiple studies, this is also something which can be tracked. So the point of DICOM is to just store medical images in a format where one could revisualize it and observe all the data to understand the context in which this image was created in the first place. However, and this is very important, this was a format created to store medical images. This was not a format created to pre-process and analyze medical images in more detail. And for that come other formats. So for DICOM, after DICOM came NIFTY. That's the Neuroimaging Informatics Technology Initiative. And this is a more newer technology. It was developed in 2003. As the name says, it was primarily made to deal with brain image data. And even nowadays, it's mostly used for MRI and fMRI data, although in principle, one could make a NIFTY file containing any medical image. One core difference while storing the data is that NIFTY would store data in a 3D or 4D format. So for example, a 3D scan would no longer be stored as a series of slices, but as one 3D slice. And you might wonder what's 4D. This usually gets important when one is studying a series of slices or a series of volumes taken over time. So one has the first 3 dimensions are the size X, and then at time Y, and then at time Z, and so on and so forth. And this can be important when studying a time series. For example, if you're observing how a tracer goes through the body or something similar to that. An example of a NIFTY image is in this format. As you can see, once it's loaded, it's not 2D. You can see the sagittal, coronal, and transverse slices. Whereas if this was a DICOM image, you would only be able to see a transverse slice with some metadata associated with it. So these are the two imaging formats which are very popularly used. There exist others. there was Analyze, which was also a format created to pre-process, post-process and analyze medical image data. This was developed roughly at the same time as DICOM, and it was the predecessor to Nifty. Where it was different was that the header, which contained the metadata, and the image data, which contained, yes, the physiological image data, was stored separately. This was used for all sorts of 3D modalities, MRI, PET, and CT. And while this technically still exists, it's mostly been superseded by the Nifty format. There are also some other imaging formats. There's MINC, ITK, PTK, NRRD. There's TIFF, which is a standard digital imaging format, but still sometimes used. I think I've seen this used for MIF images, but I don't know the details about that. But these are imaging formats which are less popular and not dealt with so much in the context of medical image processing. So far we've discussed formats. How do medical images exist in the digital world? The next question becomes, how do we load, post-process, and deal with these? So I'm going to talk now about some common Python tools for working with medical images. This is of most importance as Python is a very popularly used language for analyzing and for building quick workflows. And therefore, I'll be discussing primarily Python tooling. I won't be discussing standard viewers. I think everyone should know about them already. So the first tool, the first imaging format I discussed was called DICOM. To deal with DICOM in Python, we have the obviously named PyDICOM. How does PyDICOM work? Well, PyDICOM contains the library which reads the DICOM file. The loaded PyDICOM object is a sort of dictionary. So when one accesses a tag, it will be accessed by the PyDICOM reader, and one would find the value of the tag. So for example, ds.patient name would give you the patient name. Patient setup sequence contains multiple tags, the position, setup number, and technique description, all of which can also be accessed simply as one would access a dictionary. So you might ask, how does one actually access the image data, the raw pixels? There is actually a field called pixel array, which contains the raw pixel data. This is combined with other information to process it, such as the bit depth, the number of bits used, the intercept and slope to rescale it, because if you have a limited bit depth, you may not be able to contain all the information you need. So PyDICOM is one of the most popular libraries for dealing with DICOM images. Well, that's DICOM. The next library which I was talking about for the next format is Nifty. And for that, we have the very obviously named PyNifty. No, we don't. I misled you over there. We have one called NeBabel. NeBabel is pretty similar to PyDICOM in its format. One can simply read it. The difference is over here, one cannot simply access all the tags directly. One needs to access the header and the image data separately. So when one reads the header, for example, in the code sample on the left, one can see all the tags it contains, such as the slope, the intercept, the offsets, the slice distributions, the size of the pixels, etc. And when one reads it, one reads the image data, one has to read the image data and then apply the relative transforms, for example, the slope and the intercept and their data type and other such information. When one reads this, one straight away becomes a 3D image. One can see in this bottom right code sample, a NumPy array with 3 dimensions has been created when you read get f data. I want to give a special shout out first here to MedPy. MedPy to medical imaging is somewhat like what Keras is to machine learning. It's a wrapper around multiple medical imaging libraries. One just needs to pass it to the load command and it would, on the back end, use the specific existing technologies. There are a list of formats which are supported that contains both Nifty, DICOM series analyze, as well as specific other types of data. And as one can see on the right, when one reads a Nifty formatted file, one gets back a Nifty object. And this is important because since MedPy is a wrapper, one can simply load anything and the type will be inferred and the right library will be called by itself. Now, these are the specific tools for dealing with loading medical images. But I know what's pretty exciting to people these days is machine learning. And the question is, are we doing machine learning on medical imaging? Can we do this? Is it possible? And the answer is a sounding yes. There exist specific libraries just for machine learning and medical imaging. And I'm going to talk about now one of the biggest ones, MONAI, Medical Open Network for Artificial Intelligence. So MONAI first started off as a bunch collection of networks which are implemented for medical imaging. But since then, it's been expanded and it contains a lot of different properties. So the three main components now are MONAI Label, MONAI Core, and MONAI Deploy. Of the three, I will now be discussing MONAI Deploy in detail. So let's go to MONAI Label first. Now, when one deals with medical images, a common task is segmentation. How do we actually segment the organs, the tissues, the different tumors that we find? And there were plenty of ad hoc and custom built solutions, each of which had their own pros and cons. But what MONAI Label does really nicely is that MONAI Label is a plugin. It integrates to existing 3D tools, such as 3D Slicer in this case. And one can start to segment organs already. MONAI Label on the back end uses some machine learning techniques as well to auto-fill in after you've given some points or you've given a basic contour. And that way it really speeds up your workflow if you're trying to label a lot of medical images very quickly. The second part, MONAI Core, which was the original idea behind MONAI. So what MONAI Core does is it implements a lot of neural networks, it implements dataset structures, and it implements specific transforms, which are very necessary for medical imaging. For example, the UNet-R, it's a UNet which uses the transformer technology, which has recently become popular because of things like ChatGPT. This is implemented within MONAI. So instead of trying to implement it directly from scratch after reading the literature and introducing possible errors, one could simply call the implementation already present within MONAI Core. The hyperparameters are provided and those can be tuned according to your requirements. The transforms are another big pro of MONAI Core. There are some which are very medical imaging specific. For example, the MRI transform here performs case-based undersampling. This takes an MR image in the frequency domain and drops out specific frequencies, which will actually really help us in creating different types of data. And this is why MONAI Core has become really popular in medical imaging. Of course, there's interoperability as well. The output of, say, MONAI transform would go very well into a MONAI network, which could then be used with a specific MONAI loss function. There are some specific ones, such as the dice loss, which are very well suited to medical imaging. And in fact, MONAI has gotten so popular and so powerful that it's been integrated into NVIDIA Clara. Many of the parts of here, NVIDIA Clara, the assisted annotation, the pre-trained models, network architectures, have been taken from MONAI. And this will really help with training and deploying such models in the future on larger amounts of GPUs. Finally, we've spoken about medical images, their digital representations, tools to deal with them. And what's the last bit is the common pitfalls. Now, I'm going to show you a few examples instead of explaining the pitfalls. On the left, on the top left, one can see what the image should look like. And at the bottom, one sees the image that we've loaded. What was the problem here? The problem explained basically was the slice location attribute. When we read it, we don't know what ordering the slices are in. They could be numbered 1, 2, 3, 4, but they could be from completely different areas in the patient. And that's one of the disadvantages of DICOM series. For this reason, DICOM metadata usually contains a metadata parameter saying the slice location attribute. When one sorts according to the slice location attribute instead of according to the file name, one gets the image that's in the top left, which is perfect and well loaded and is not scrambled like the one below. And the second and last common problem I want to show you today, there seems to be some sort of very strange line artifacts in the lower image. How did this happen? Well, again, the DICOM metadata contains tags explaining a rescale intercept and a rescale slope. When we load the image, we sometimes do not rescale it correctly. We simply put the raw pixel values. And if they are not properly scaled, one would get very varying intensities within the same problem. And therefore, one should look out carefully for rescaling them with the slope and then removing the intercept, which is an offset. So these are two of the most common problems which I've encountered while dealing with medical images. So that's all that I have to discuss today. I've shown you some medical images, some of their digital formats and representations, tools to deal with them, tools to load them, problems one can have while loading them, and how to deal with them in the machine learning context. Thanks very much, and I'm happy to take any questions.